Good morning or good afternoon, distinguished session chair, fellow researchers, and college. My name is Niken Aisal Sabila from the School of Industrial Engineering, Telkom University, Bandung. I will be presenting our work titled Multi-Tenant Backend Architecture for IoT-Based Postpaid Smart Water Meter Monitoring and Billing System. In short, this paper proposed a modular backend architecture that brings together IoT telemetry ingestions, multi-tenant data isolations, and asynchronous postpaid payment asynchronizations into a single unified platform. I will cover the research gap, our methodology, and for contributions, the system architecture and its actors, our validation and load test result, and finally, the discussions and conclusions. Vertical residential buildings are growing rapidly, but most water utilities still rely on manual meter reading and conventional postpaid billing. This process is slow, error-prone, and can contribute significantly to non-revenue water. The literature shows four main gaps. Smart water meter research focus mainly on telemetry, multi-tenant research focus on software as a service, isolation rather than IoT. Payment research often overlooks water utility operations, and the existing system integrates all three aspects: telemetry, multi-tenancy, and payment synchronization into one platform. Existing smart water meter systems are commonly prepaid and single-tenant, requiring a separate database for each unit. Our architecture is postpaid and multi-tenant, using one shared platform with logical data isolations built on Node.js, Express.js, PostgreSQL, and Prisma Object Relational Mapping. There are four main contributions. First, a unified backend architecture integrating telemetry, multi-tenancy, and billing within one platform. Second, continuous IoT telemetry ingestions through representational state transfer application programming interface. Third, a logical multi-tenant database using PostgreSQL and Prisma Object Relational Mapping within a single shared database instance. And fourth, asynchronous webhook-based payment synchronizations that avoids periodic polling and its potential concurrency issues. We use the prototyping method in 5 stages. First is communications, to gather requirements from 4 actors. Second is quick plan, to define the functional requirements and use case. Third, modeling quick designs, to design the architecture and dashboard. Fourth, constructions of prototype, to implement the representational state transfer service. And fifth, deployment, delivery, and feedback for functional validation and K6 lab testing using 100 and 300 virtual users. For modules for the systems. The first is IoT telemetry ingestions, which validates and stores data from smart water meter devices. The second is multi-tenant data management, which logically isolates tenant data through Prisma Object Relational Mapping. The third is postpaid billing generations, which automatically calculates bill for each billing period. And the fourth is asynchronous payment synchronizations, which updates payment status through sended webhooks. The four actors interact with the systems. The administrator monitors consumption and manage devices, unit, and billing records. The end users authenticates, view bills, and makes payments. The smart water meter device sends telemetry autonomously and periodically, and the payment gateway sends it, process transactions, and confirms the payment status through a webhook. We used KSIG to test 100, 200, and 300 virtual users with 3 runs for each scenario and 2 minutes per run across 5 endpoints: login, dashboard, billing statistics, billing table, and IoT usage. We focused on 95th percentile latency, which better reflects the experience of slower requests than the average response time alone. All 7 core service-based validation through Postman with 0 functional errors. This service includes authentication, telemetry ingestion, dashboard monitoring, unit management, billing generation, invoicings, and payment verification, and all performed as expected. We also validated the webhook flow directly. The payment status starts as unpaid. After the webhook is processed, it returns hypertext transfer protocol status code to hundreds, and the billing status is correctly updated to paid. This confirms that the asynchronous payment synchronization works reliably. Security hardening, including token verifications, transport layer security, and idempotency checks, remains part of our future work. Under load, the average response time increased from 171.77 milliseconds at 100 virtual users to 998.98 milliseconds at 300 virtual users. This represents an increase of nearly 6 times, while throughput decreased from approximately 410 to 251 requests per second. Importantly, no connections or drops. This indicates that the main bottleneck is located in the application and database layers rather than the network. The 95th percentile latency, representing the latency experienced by the slowest 5% of requests, increased even more significantly. It rose from the 365.85 millisecond at 100 virtual users to 1,815.91 milliseconds at 300 virtual users. The widening gap between the average response time and the 95th percentile indicates that response consistency degrades faster than the average alone would suggest. There are 4 main takeaways. First, performance remains comfortable under moderate load, particularly at around 100 virtual users. Second, heavier load mainly result in slower and less predictable response rather than system failures. Third, write-intensive endpoints such as IoT usage experience greater degradations than read-only endpoints such as dashboard. And fourth, the main contributions of this study is integrations, unifying telemetry, multi-tenancy, and payment synchronization rather than introducing a new algorithm. In conclusion, all 7 services were validated with 0 functional errors. The webhook-based payment synchronizations perform reliably. This, the system remains stable under 100 virtual users, while response time increases nearly 6 times at 300 virtual users. The 95th percentile latency increases even more significantly and write-intensive endpoints experience the greatest degradations. The proposed architecture is suitable for moderate workloads. However, horizontal scaling would be required to support thousands of devices. The study was evaluated in a controlled environment using one payment gateway sending. Future work includes database optimization, resource analysis, horizontal scaling, and support for additional payment gateways. Thank you for your attention. I sincerely appreciate this opportunity to present our research to you.